Hi, thanks for joining my PETS 2022 presentation on our paper called From Onion Not Found to Guard Discovery. I'm Leonard Oldenburg, and this is joint work together with Ganesh Asar of Radboud University and Claudia Diaz of KU Leuven. Tor is the largest deployed anonymity service that we have available. Users of Tor can use Tor browser to browse the web privately by relaying their traffic through Tor. Connections to the public web are typically relayed through a chain or circuit in Tor of 3 Tor relays. So users in this case select a guard, then a middle, and then an exit, through which to tunnel their traffic through towards the public web DNS or web servers. Guards on these circuits have a particularly important position because they know the IP addresses of their users, and users stick to them for longer amounts of time. There's also connections within the Tor web, so destinations reached by connecting to Onion addresses. And Onion services offer also the server-side privacy protections that users enjoy as well. Connecting to an Onion service is a bit of a complicated process involving multiple protocols. However, we will only focus on the first step, so the descriptor lookup at hidden service directories or HSDIRs, because this is relevant to our attack. Downloading such descriptor is relevant because connecting to an Onion service is a bit more involved and more information is needed for how to reach out to them. You can think of this step as somewhat like DNS but for Onion services. Crucially for our attack, any descriptor describing for how to connect to an Onion service is located at 6 hidden service directories or HSDIRs, such that if any one of them is down, there's backup ones that users can reach out to and still be able to download the descriptor of the service. And also relevant for us is that each lookup for such a descriptor is done via a fresh 4-hop circuit. So let's look at how a lookup is done from the client to the hidden service directories in the case that the Onion service address requested by the client does not exist. So there's no descriptor for this Onion service address. You can see here a Tor browser user reaching out to one of the 6 hidden service directories responsible for maintaining the hidden service descriptor of the address attack.onion. Attack.onion does not exist, so the hidden service directory cannot respond with anything that the user can use to connect to the service, and thus responds with 404 not found. When the victim receives such a response, it will continue to the next hidden service directory out of those 6 and ask again for the descriptor of attack.onion. Again, the hidden service directory does not know about this particular address, so it will respond with 404 not found. This process is repeated until all 6 hidden service directories have been contacted by the user, always receiving a negative response, and then the lookup is abandoned. For our attack, we consider a broad range of adversaries that only need to provide a couple of capabilities. First, we assume that they serve a fraction of Tor's total relay bandwidth. For example, 1%, 2%, or 5% of Tor's relay bandwidth. Additionally, the adversary needs to run a few of those hidden service directories or HSDIRs, but a small number such as 10 or 20 of them suffices. And finally, the adversary needs to somehow be part of the attack webpage that victims will visit. And this can happen by them being the first party or by being a third party included in the page, such as an advertiser. And our attack is based on the unregulated behavior client side to look up hidden service descriptors and the distinctive cell pattern of such unsuccessful lookup, so where the response is 404 not found. We exploit this for a guard discovery attack, and we also evaluate countermeasures to help mitigate the impact of our attack. So let's look at how it works. You can see here a Tor browser victim first requesting the target web page, just via a regular 3-hop circuit. As part of the target web page, the adversary is somehow being able to control parts of it and will embed a malicious script into the web page. In step 3, you can see how when the user receives the response from the web server, this malicious script, being part of the response, starts embedding non-existing Onion service addresses into the web page. Through a large number of live Tor network experiments, we determined that embedding at the rate of 3 non-existing Onion service addresses per second results in the highest overall number of lookups done by clients. Step 4 is exactly the process that I described a couple of slides ago. So the victim Tor browser will start creating many of these fresh 4-hop circuits to hidden service directories in order to download the descriptors of these allegedly existing Onion services. At some point, the adversary is going to be part of one of these lookups in the second position and in the HSDIR, so the fourth position. And this is important for the adversary because this will allow them to ultimately discover G1 being the guard of the victim. The adversary keeps track of any of the cell patterns of the lookups that it sees, and also whether, for example, at the hidden service directory position, the request was for a target address or not. Crucially though, in step 6, you can see that the adversary always responds according to protocol, so does not mess with the lookup. So it will respond with 404 not found to any of the requests that it does not know the descriptors for, including the attack addresses. When the adversary sees a lookup for a target address at the hidden service directory position, it will reach out to all its middle relays, such as in this case R5, and put together the two views, only selecting the instances where a target address was requested and the cell pattern at the second hop matched the attack cell pattern. Additionally, there's a couple of more checks about metadata for this request, but ultimately the adversary will be able to note down G1 as the candidate guard for the victim of this attack. We use simulations to show how fast our attack is, and we do this by a victim visiting the target attack webpage, and then we tracking the time that it takes to discover the guard of this victim. We take a couple of adversarial settings into account, such as the bandwidth share B that the adversary contributes to the Tor network. Again, this is between 1%, 2%, or 5%. Also, we consider the share of the hidden service directories for any of the onion service addresses that are under adversarial control. So in this case, this can be 1 out of 6 that we consider, or 2 out of 6, or 1 over 3. And also for legacy V2 onion services, we include the setting where all of the hidden service directories for a particular address are under adversarial control. This is not relevant for V3 onion services anymore that are the standard now. For this setting, we consider 1 over 3 to be the most realistic and, in this case, strongest adversarial setting. Of course, users also do unrelated background lookups that result in 404 not found responses. And we have to consider the rate of these background or noise lookups, because they may potentially lead to false positives on the adversarial side. So we do an experiment and use an estimate of this noise lookup rate in our simulations. From our live Tor network experiments, we have collected a large number of actual lookups that we reuse for our simulations and base our requests in the simulations on. And then ultimately, it is important that we track seeing a guard twice for the adversary. So we want to note down the occurrence of a particular guard twice for a victim before we make a decision, because this drives down the false positive rate. So looking at the main result plot, this is a cumulative distribution plot, and you can see that the strength of the adversary increases from top left to bottom right. In the columns, you have the share of the hidden service directories that the adversary controls, and in the rows, you see the relay bandwidth share of the adversary. And for the adversary that we consider realistic and strongest in the current Tor setting, H over 1.3 and B equals 5%, we see that after 12.06 seconds, the adversary has discovered the guards of 50% of the victims, and it takes the adversary less than 50 seconds to discover the guards of 99% of all the victims. The total number of simulations done for this plot is 2.5 million. In terms of countermeasures, we consider two approaches to mitigate the impact of our attack. The first one tries to limit the number of circuit building attempts that clients can do before being regulated or throttled. So this is an approach to cap the number of attempts. And the second approach tries to rather restrict the set of relays that are eligible for a particular position on those circuits. So this goes towards reusing prior made choices for future attempts. And these map nicely onto our countermeasures that I'm showing here on the slides. The first one is that we propose to include a token bucket at the Tor browser tab level that will result in the Tor browser tab always having to take a token when trying to build such lookup circuit. And when the token bucket is empty, no more attempts can be done. And the second approach is actually a proposal by the Tor developers called Vanguard's Lite. and Vanguard's Light applies the concept of guards to the second hop position on onion circuits. So it restricts the set of eligible relays for this position from potentially all Tor relays to a set of 4 chosen by the user for a particular amount of time. And this naturally limits the exposure of Tor users to the ones that have at least one adversarial second hop guard. And Vanguard's Light was implemented, deployed in Tor 0.4.7 line. Looking at the results, we can see that the token bucket countermeasure is quite effective against our particular attack. So against the adversary controlling 1/3 of all the hidden source directories that are maintaining the attack addresses, and for various initial values in the token bucket, so this is the rows, we see that after 5 minutes of attack time, compromise probabilities are between 1% for an initial value of 5, 2% for an initial value of 10, and 4% of an initial value of 15. So this is down from beyond 99% compromise probability. Vanguard's Light it presents a different picture. So in the case that Tor users chose at least one adversarial relay as part of their second hop guard set, compromise is quick. You can see here that after 21.31 seconds, 99% of the victim's guards have been discovered by the adversary. However, this is limited to only the set of Tor users that actually selected adversarial relay in the second hop guard set. And this applies to, on average, only 18.5% of Tor users for the 5% bandwidth share adversary. The remaining Tor users are fine. Thank you very much. This was my presentation. You can find code and data at this location, and I'm happy to take questions.